Okay, hi everyone, and good morning, good afternoon, good evening. I hope I covered everything. Welcome back. And in Andreas' case, I guess, welcome. So today's lecture's topic is basically rudimentary model theory. So if you're a logician, basically apologies for having to listen to this. Essentially, we will just rehash certain ideas, some very, very basic ideas, I should say, from model theory over and over and over, and see that they actually have non-trivial implications to C algebras. What you see on your screens is a quick recap of Monday's lecture. So let's go over it quickly. Last time we defined this algebra F sub A, the algebra of formulas over A. I'm not going to repeat the definition, assuming that you remember what it was, but just quickly, atomic formulas are just norms of star polynomials. And from those atomic formulas, we form more formulas by applying continuous real functions on those formulas, and also applying quantifiers sup and inf. Sup and inf come with a domain, so we are taking sups and infs only over bounded balls, and because of that, every formula by induction on complexity has to it attached modules of uniform continuity. So regardless of where you're interpreting it in what's its algebra, you always have uniformly continuous function. On every bounded ball, it is uniformly continuous, and you know what the modules is in advance, regardless of what the algebra is. Now that algebra of formulas denoted F sub A, this A is a C-star algebra that we use for constants, so those star polynomials are allowed to refer to elements of A. That is algebra, it is a real algebra over R, and it is equipped with a semi-norm, so norm, semi-norm of a formula phi is supremum taken over all C-star algebras B, which have A as a subalgebra or as unital subalgebra. If A has a unit, we insist that that unit is what it is supposed to be. And also over all B bar of the appropriate sort, right? So belonging to the right bounded ball. We just evaluate phi there and take the sup of the absolute values. This is a semi-norm. And we just mod out by zero sets and take completion, and that is this M sub A. So this is the real Banach algebra of formulas, and we proved last time two basic results about this. First one is Walsh's theorem, that for any formula in any F sub A, if you have an ultra product, then to evaluate formula in the ultra product, you just take limit along the ultra filter of values of the formula, and that's it, right? So evaluation is as simple as you can possibly hope it to be. We also define the type. Now, this is important definition. We'll spend a lot of time on it. So let me just say a few more things about it. Again, you have this algebra A, over which we are considering formulas. There is this big algebra C, which may or may not be saturated. That doesn't really matter. And now we have some element B of C. It could be a tuple, but let's just think of it as an element. How do we evaluate its type? Well, type is a character whose domain is the algebra of formulas over A. So here I put F sub A, I could put M sub A as well, it really makes no difference. What matters is that these are formulas that fit B, that they have three variables that are exactly of the same sort as B. And how do we define a function on this algebra? Well, any formula is sent to evaluation of that formula in the algebra C. So this is really a character, so it's homomorphism into the real numbers, which has norm 1. And it tells us many things about B. As I said last time, it tells you whether B is invertible. If B is a pair of unitaries, it tells you whether they are homotopic, and things like that that you cannot really see from the formulas. But there was an alternative definition of type to think of type as set of conditions. And here is what a condition looks like. So on the left-hand side, you have a formula phi of x bar. On the right-hand side, there is just a real number. So this is very similar to what we did with degree 1 types. And such a set of conditions can be identified with a character. Basically, conditions determine what the kernel of the character is. Right, phi of x bar minus r is in the kernel if phi of x bar is supposed to be r. And therefore, we have type as a set of conditions or type as a functional. Those are interchangeable. Modulo one fact that I haven't mentioned last time, but now I should say it. In model theory, one distinguishes between complete types and partial types. The interesting types for us here are the partial types. Complete type would be a type that tells you exactly for each formula what is its value. Or in other words, if you like to think of it as a functional, it is functional whose domain is the entire algebra of formulas. But those types tell us too much. Instead, partial types are just sets of conditions. Now, just like what we had in degree 1 case. Now, if you like to think in terms of characters, well, basically, you just look at all conditions which occur in a type, collect all those formulas, phi minus r, which occur in those conditions, and just form a subalgebra, generate subalgebra by those formulas. And then your type really defines character on that subalgebra. Right. Okay, so algebra C is countably saturated if every countable, approximately satisfiable type over C is realized in it. What we proved is that if you have a countably incomplete ultrafilter, which is any non-principal ultrafilter of natural numbers, then any ultra product of C-star algebras with respect to that ultrafilter is countably saturated. And because of that, we get all sorts of consequences. So, okay, so it was a quick recap of what we did last time. So a few more things that I need to say. Let me draw this. So again, we have the same picture as in the previous slide. We have C, A is a subalgebra, B bar is some n tuple in C. Now, type of B bar over A, its kernel is just phi of x bar minus r, where these pairs phi r range over all conditions satisfied by B. Now, this has a consequence that is basically closer to functional analysis than to classical model theory. C-star algebra C is countably saturated if and only if for every n and for every separable subalgebra A of C, this set. So what is this? This is the set of types of all n tuples over all n tuples in C over A. That subalgebra is weak star closed. sorry, not subalgebra. This set of characters is weak star closed. Let me draw a picture. Here C, here is A, right? So you look at different B bars. Why is that so? You see, essentially countably saturated means that every approximately satisfiable type which is also countable, is also realized in the algebra. Now, if you have approximately satisfiable type which is countable, look at its domain, this subalgebra of F sub A, on which it is a character. What does approximately satisfiable mean? Well, it means exactly that it is a pointwise limit of types of elements in the algebra. Right? Because approximately satisfiable means for every finite subset of the type, for every epsilon, there is an element such that if you evaluate those conditions in that finite subset, you get up to epsilon the right values, which is exactly description of weak star open neighborhoods of this type that we have here. Right? So in other words, the weak star closure of approximately satisfiable types is exactly, the weak star closure of realized types is approximately satisfiable types. So let me write it down. So that's probably something that should be on the slide. So the weak star closure of type over C, B bar over A for B bar in Cn is the set of approximately satisfiable types over A. Right, from there, if you just parse the definition, C is countably saturated if and only if exactly for every separable subalgebra of C, this set is weak star closed. The only thing that I haven't said yet that I've been using is that if you have a countable type, then what it means that those formulas which occur in it, they generate a countable subalgebra of C, and vice versa. If you have countable subalgebra of C, then you can find a countable dense set of formulas in F sub A, and therefore you just care about countable type. This is something that we use several times before when we were finding countable types which do one thing or another. Okay, so this is basically just saying what I just said. So type is identified with a function of T tilde, so that T tilde sends phi to R for each condition of this sort. And then this is what I just said, right? So it's type is approximately satisfiable if and only if it is in the weak star closure of realized types. Right, so this is basically partial justification of what I said before, that continuous model theory is really functional analysis. And I should emphasize here that this has nothing to do with cyst algebras. This is just a general fact of continuous model theory. Okay, so let's take a look at some variations. We said formula is quantifier free if it does not involve quantifiers sup or inf. In other words, formula is just of this sort. It is f of some tuple of atomic formulas psi. And remember, atomic formula is just norm of some star polynomial. Now, these formulas again form an algebra, right? All that matters is that they're closed under multiplication by scalars, multiplication between them, and addition between them. So it's again algebra over R, right? It's a real algebra. And we can just repeat all the definitions that we had before for quantifier free. So A quantifier-free condition is a condition in which a formula is quantifier-free. Quantifier-free type is a set of quantifier-free conditions, or you can think of it as functional on the algebra of quantifier-free formulas. And quantifier-free saturation, right? So it's every quantifier-free, countable, approximately satisfiable type is satisfiable. And you can also be a bit more pickier or finer, right? We defined the degree 1 conditions maybe a week or so ago, but for any n, you can define degree n conditions. So one interesting case that we actually mentioned, so degree 2 condition is something like norm of x star x minus 1 is equal to 0, condition which tells us that x is an isometry. And if you add this condition, x star minus 1 is equal to 0, together these two conditions tell you that x is a unitary. And as we saw, you cannot express the fact that x is a unitary in degree 1 way, because the Calkin algebra is degree 1 saturated, but there was this observation of Chris Phillips that there is a type that can be approximately realized by unitaries, but not satisfied by a unitary. Right? So there is no clever way to somehow mimic degree 2 condition. Well, no, not these conditions in a degree 1 fashion. So you can define, degree 15 conditions and whatnot, and then you can look at hierarchy of different saturations, right? So the full saturation is on top. It implies quantifier-free saturation, right? Because you're just asking for less. And degree n plus 1 saturation implies degree n saturation, and all the way down to degree 1 saturation. Now, the question is which, if any, of these arrows are reversible? Okay, we already saw that this one here is not. Now, what about degree 2 versus degree 3? Well, it is, here is a cute little fact that degree 2 saturation implies degree 3 saturation. So what is the trick? Well, whenever you see a condition that involves something like, x, y, so in any condition which involves product x, y, you can just introduce a new variable, z, and just throw in a condition which says x minus 1, xy minus z is equal to 0. So you can just go through all of your polynomials. Wherever you see a product of two variables, you can just introduce a new variable. Actually, I can call it zxy to avoid any ambiguity, and just throw in more conditions. And that way, if you have something like xy squared, for example, this becomes equal to zy, right? So you lower degree from 3 to 2, well, you just do it countably many steps to remove all the higher products, and show in that way that every degree 3 type is equivalent to degree 2 type, which has additional variables, but additional variables are not really a problem. And even if you end up with countably many variables, it is not a problem, because as we saw, you can always handle countable types, so you have countably many variables. Equivalence of types is I guess it's clear what I mean. One is approximately satisfiable if and only if the other one is approximately satisfiable, and the same for satisfiable. So by this little trick, you have that degree 2 implies degree 3, But then there was nothing special about degree 2 and 3. All that one needs really here is to have at least 2, right? So that you can talk about conditions which involve product of 2 variables. Once you have that, then you can reduce degree 4 to degree 3 and to degree 2 and so on. So all of these arrows are reversible. Once you have degree 2, you have degree n for any n, you have degree n plus 1, and actually with a little bit more, you can go all the way to quantifier-free saturation. So everything between quantifier-free saturation and degree 2 saturation is really just one thing. They're all equivalent. Which is why we don't have any examples of algebra which is degree 2 saturated, but not much more than that. Okay, and now you may wonder, what about quantifier-free saturation versus saturation? And there is an example. So here is, I mean, you've seen part of this proof essentially. Let me just read what it says. If C is countably saturated, so C is fully countably saturated, and if you have a separable subalgebra, say is a separable C star subalgebra, look at the relative commutant. It is still countably quantifier-free saturated. This is exactly the same trick that we use to prove analogous statement for degree 1 saturation. So let me just recap the trick once again. You have this relative commutant, you have type over that relative commutant. Well, you just add countably many conditions to that type, asserting that your variable commutes with everything in A. That's even degree 1. It's definitely countably saturated. And this type is again approximately realizable in C this time. But now realization of that type in C is going to belong to commutant because you made sure that everything is commuting with A, right? So any quantifier-free type over this algebra can be turned into quantifier-free type over C, and therefore realized by countable saturation of C. And this is very important that A is separable, right? You just need to add countably many conditions. If A is non-separable, this is not true. Now you may wonder, what about full saturation? Well, you see, the point is that you cannot handle quantifiers if your formula involves something like supremum over norm of x less or equal than 1. Well, you want to take supremum over the unit ball of A commutant intersected with C. There is no obvious way to somehow refer to this set A commutant intersected with C as a subset of C. So this is really the issue of definability in model theory. There is a concrete notion, maybe unfortunately named, of definable set, which are sets over which one can quantify. These are just not of that sort. And there is actually an example that you can find concrete C and concrete separable subalgebra A, so that this relative commutant is quantifier-free saturated, but not fully saturated. Yeah, and if anybody wants to hear the proof, I'll be happy to talk about it. Okay, so back to the generalities. As I said, proofs of Washer's theorem and countable saturations have nothing to do with C-star algebras. So they're just general theorems talking about arbitrary metric structures. So there is a technical notion of what exactly is a metric structure. Instead of defining it, I'll just take a look at two relevant examples for us here. So here is the first one. Before that, I need to introduce some definitions. So a state on a C-star algebra is a positive functional of norm 1. Now, what positive functional means? It means that if you look at the positive part of your C-star algebra, this is subset of non-negative reals. States are quite important in algebras in theory of C-star algebras for representations, representation theory in particular. Basically, certain cyclic representations of C-star algebras are coded by states. We don't need that. All that I need is tracial states. So state is tracial if it has this property that tau of AB is equal to tau of BA for all AB in A. The prime example is think about n by n matrices and think of the trace. Trace of matrix now, the only wrong thing with the trace is that it is not of norm 1, it is of norm n. So you just need to normalize it, to normalize by multiply by 1 over n, and then you get positive functional, which is a tracial state. And on n by n matrices, this is a unique tracial state, which is essentially effective linear algebra. Another example of tracial C-star algebra is a tensor product of M2s. Nothing special about number 2 here, of course, right? The so-called car algebra. The tensor product of tracial states is a tracial state. This algebra also has a unique tracial state. These tracial state sets of tracial states can be much more complicated than that. By T of A, we denote the set of all tracial states of A. Now, this T of A, it is obviously subset of the dual space. And because they are of norm 1, they are all, so it is a subset of the unit ball of the dual unit dual ball, and it doesn't take long to see that tracial states are weak star closed. Therefore, by Banach-Haloglu theorem, this is a weak star compact subset of the unit ball, and it's also convex. Convex combination of the states is a state. Convex combination of traces is a trace. So this is a nice compact convex set. It's even nicer than just compact convex. It is what is called a Choquet simplex, but we don't need to go there. So all that we need to know is that certain C-star algebras have tracial states. Not all of them. Now, here is definition. Unital C-star algebra is said to be finite. This is somewhat unfortunate terminology, but actually it makes a lot of sense if you think about it. If there is no element V such that V star V is 1, so V is an isometry, and V star is less than 1. So it's a proper isometry. It is said to be stably finite if Mn of A, so this is the algebra of n by n matrices over A with natural operations, if this is finite for all n. Now, it is not obvious for sure, but there are examples such that A is finite and M2 of A is not finite. There is even a simple nuclear example of such A due to Mikler-Rordam, which is a beautiful application of all sorts of things, including some non-trivial combinatorics. So one has to distinguish between finite and stably finite. Now, why do we care about finiteness? Fact easy to prove is that if A has a non-zero sorry. No, this is not true. Sorry, I just realized that this is not really. What am I missing here? Okay, so I'll just make a patch here. If this and A is simple, there is definitely a non-simple counterexample. Right. Okay. Yes. Exactly. Right. So this is what I should have written. So if A has a tracial state, and it is a simple C algebra, then it is stably finite. This is an exercise, and actually, I'm going to give you a great hint on the next slide. So if you're just a little bit patient, you can wait and see, and you'll see what's going on. So we have this. Now, question is, do we have a converse? So this is, I'll just write here plus a simple. So the converse, does stably finite imply tracial, is a well-known open problem. And there are deep partial results by Hagerup, Kirchberg, Hagerup, Thorbjornsen. Now, what I would like to point out here is that A being finite or not being finite can be expressed by a formula. So A is not finite is, if you take this formula Psi, so this is Psi, look at infimum over all x's of norm 1, of norm of 1 minus x star x plus absolute value of 1 minus norm of 1 minus x star. When is this 0? So you see, if Psi is 0, and if that 0 is attained, let's not worry about the fact that this infimum is not obviously attained always. Then x has to be an isometry, right? X star x is equal to 1. And moreover, x star is not equal to 1. And that's exactly what this here says. Now, the fact is that for certain formulas, this one in particular, this infimum is attained, which is an application of continuous functional calculus. Basically, trick is that once you get close enough to 1, once you're at distance less than 1 of the unit, you're invertible. And once you're invertible, then you can just modify x by countable continuous functional calculus and get something that realizes this formula on the nose. Okay, so what this means is that finiteness is preserved by alpha powers, and so it's non-finiteness, and so on. Sorry, no. A is not. What this means is that non-finiteness is preserved by ultra powers. Finiteness is for finiteness, it's not obvious, and I guess it's probably not even true. But okay, I'll leave it at that. Any questions? Okay, so if you have a tracial state tau, then you can define this expression here on C algebra. Tau of A star A square root of that. It is a semi-norm of A on A. And this is actually a semi-norm that behaves like a Hilbert space semi-norm. It's really, it turns A into pre-Hilbert space. This ideal of all A's which have semi-norm 0, it is an ideal, and what I mean by ideal here is a two-sided norm closed, therefore self-adjoint ideal of A. Right, so tracial state, if you have tracial state, then if algebra is simple, this J tau is going to be a trivial ideal. Okay. Now, again, if there are, if tracial space of A is non-empty, then you can define this uniform tracial norm, U stands for uniform, to be the supremum over all tracial states of this. Right. So if you have more than one tracial state, this is going to be some semi-norm. And again, you have this ideal, which is the intersection of all the ideals for different tracial states. It is, again, an ideal of A, the tracial ideal. And now you may wonder how this tracial semi-norm relates to the original operator norm. Note, first thing to note is that there is an inequality this way. This is less equal than the operator norm because remember, tau has norm 1, right? So like any other state. So this is dominated by the operator norm. And here is a little exercise. If you have an abelian cyst algebra, then the operator norm and the uniform tracial norm agree on A. All you need to know is just remember what abelian cyst algebras look like. Now, here is important bit to keep in mind. Uniform tracial norm is uniformly continuous with respect to operator norm, right? It's actually less or equal than it. It's one Lipschitz, but not vice versa. Well, in some situations, vice versa is true, right? If they agree, then definitely they are absolutely continuous with respect to each other. But in interesting situations, when the algebra is simple, it is not true that the operator norm is continuous with respect to the tracial norm, which is important for reasons that will soon be clear. Okay, and now we come back to ultra products. So what is the idea here? Well, I have my cyst algebra A, which has this tracial space. And now I just discard the operator norm and just look at it as a structure with respect to the uniform norm. And just apply the model theoretic machinery to this. So this is just a special case with more general definitions. Suppose that U is an ultra filter of some index set. AJ are unital cyst algebras with non-empty tracial simplices. Now look at this ideal, J sub U, which is all A in the product, such that along the ultra filter, the uniform tracial norms converge to 0. This is again two-sided self-adjoint norm-closed ideal. So again, basically, one way to see that is by going for a moment to the previous slide. Right? So this J is an ideal. Really, you're taking ultra product of J ideals for different A sub J's, and it is going to be a two-sided ideal. You also check it is norm closed, and therefore we can take, when I say norm closed, I mean even operator norm closed, right? So it's we are talking about two different norms here, but because the two norm is dominated by operator norm, it's going to be closed in both. And now we can form this quotient. This is J, this should be J. So this quotient is called the tracial ultra product associated to this ultra filter U. So if all AJs are equal, then we call it ultra power. So here I have some references. This structure was very important in the classification program recently. Probably Chris Schaffhauser's paper is a great place to start if you haven't seen this. But there is a major progress recently by Castillejos and others. I think it's a 6-author paper, in which these structures are being used in a very, very subtle way. Now, what I want to do right here is just see what model theory can tell us about these structures. Before I go on, just note that in this structure, we don't have operator norm anymore, right? So we are just not taking it here because it is not uniformly continuous with respect to the tracial norm. So in the ultra power, you would just have difficulty extending it. Another thing is that this norm here, it is a Banach space norm, but it is certainly not a Cist algebra norm and not even a Banach algebra norm. So we're really looking at Cist algebras in disguise. They have this other norm, and Cist algebra structure is somehow hidden behind properties of that norm. But nevertheless, even though by Walsh's theorem it's not obvious, actually still we don't even know that Walsh's theorem is true, but you know, it is not obvious why this should be a Cist algebra if you think like a model theorist. But if you think like a Cist algebraist, it is obvious because you have a two-sided norm-closed ideal. So quotient is a Cist algebra. Now what that has to do with original Cist algebra, that is a different question. Here is let's try to answer that question. So basically, this is the definition that you've seen before, but we are revisiting it with a slight tweak. So A here is separable Cist algebra. A of x bar is algebra of star polynomials in x bar with coefficients in A. They're called terms. And now we assume that A has a non-empty tracial space and that it's unital. And now we define formulas recursively. If you just look at this definition, it looks very much like the old definition. So there are only two differences. Actually, there is only one difference, really. So I'll just swipe to the next slide. So here it is. You see the atomic formulas, they are now expressions of this form. You're taking two norm of a star polynomial. And the other two parts of definition are identical. You can apply continuous functions and you have quantifiers, sups and infs. One important bit here is we are taking sups and infs over norm, operator norm unit balls. Operator norm is still present in the definition of sorts, if not in the language. Now, and also this space, I call it FA sub T. I should say this is just ad hoc notation only for this course. So this space again has an algebra structure. So pretty much everything that I said about that space applies for this situation. You can also mod out by this and get real Banach algebra and so on. We want to talk about interpretation. So we have a formula phi, which is a tracial formula over A. A is a subalgebra of B. Tracial simplex of B is non-empty. And B bar in B is of the same sort as X bar, which just means the range over the same bounded ball. The interpretation is defined by recursion on complexity, right? So terms are just interpreted by evaluating star polynomials. Then you just evaluate uniform two norm at those polynomials and then apply continuous functions and take sups and infs over bounded balls. So that is recursion, that's definition of formula, and everything still holds. Every formula comes with a modulus of uniform continuity. And also what really important for us is Walsh's theorem and countable saturation still hold. So I just stated them here, right? So it's the same theorem, but just for different language. So if A is a subalgebra of each A sub j, they are all unital. Tracial simplex of each A sub j is non-empty. U is an ultrafilter. Phi is a formula, tracial formula over A. And C is the ultra product. This is tracial ultra product. Then the value of phi in the ultra product is just limit along the ultra filter of the values in these factors of the ultra product for any a bar of the appropriate sort. Proof is identical, just induction on complexity of phi. So I'm not going over it once again. Second, suppose that U is countable incomplete ultra filter, and you have unital C algebras with tracial simplices non-empty. Note here I'm not talking about A. I don't want to commit to this separable subalgebra A. Then this ultra product of those algebras, the tracial ultra product, is countably saturated. But here in red, with respect to the tracial language CT, I cannot overemphasize this. We'll come back to that in a moment. You see, if you just say this C algebra is countably saturated, it means all sorts of things, right? We already went over tons and tons of consequences of this. Well, here you should be careful not to say this C star algebra is countably saturated. It is not countably saturated as C star algebra. It is countably saturated as a tracial C star algebra, and there is a difference. And we'll see what it is in a moment. Any questions? As you can see in this, in today's lecture, basically there are no proofs. I'm just repeating what I said before, but these are things that should be said. So you can think of it as a recap with a twist. Okay, corollary. If U is a non-principal ultra filter on natural numbers and you have a sequence unital C algebras, each one of them tracial, and you form tracial ultra product, then C is countably saturated with respect to tracial language. Now, what that implies, it is SAW star, it is crisp. I have the ellipsis here. I have to admit, until I started preparing for this lecture, I actually never checked which of those properties are still true. I checked the first two, it is probably a good project just to see what remains, what doesn't remain, and just to see that something non-trivial is going on. We have this question here. If A is an element of C, C is as in the corollary. A is a positive contraction, 0 is in its spectrum. Can we conclude that the annihilator of A in C is non-zero? This was one of the consequences of countable degree 1 saturation, right? So it's the saturation which is at the very bottom of this hierarchy. Now this one is fully saturated, but in different language. You could say it's wrong language for this sort of thing. So let's see what happens here. Remember what was the type that witnessed that the answer was yes for degree 1 saturated C algebras, degree 1 saturated in the norm. So type, just really it was rather simple. It was just saying that norm of XA is equal to 0. And the other condition was just saying that norm of X is equal to 1, where 1 is a randomly chosen number greater than 0, right? It's as good as anything. By using continuous functional calculus, we saw before that this type was approximately satisfiable because 0 was in a spectrum of A in the case of the norm. Now, here in the tracial language, well, we can try to do the same. Just say this is equal to 0. Well, this is pretty much the same. I mean, you can add other. Oh, yes, that's right. Actually, we had to add the other one. Also this, right? You want it from both sides. So you can do it from both sides. That's fine. But you also, if you also want to say this, then you get into trouble because this norm is too small. And if you think about the argument using continuous functional calculus, why this type was satisfiable before, the argument breaks down. So let's see what happens. Right, okay, so this is not necessarily. So here is the example. Take the car algebra, M2 to infinity. Now, tracial space of this algebra has exactly one element, this unique tracial state. And we can take C to be the power, tracial ultra power. It also has only one tracial state, but that's not really important. Choose any A in A plus, so A is the car algebra, which is a positive contraction, so it has spectrum 0, 1. And also I want this tracial state restricted to C star of A to be the Lebesgue measure. What do I mean by this? Well, C star of A is by continuous functional calculus, just continuous functions on 0, 1. Right, so this is the algebra generated by A and the unit, I guess I should say, C star A comma 1, right? So you want to throw a unit. And what I mean by it being Lebesgue measure? Well, I mean that if I have any function f, which is continuous function 0, 1, that tau of f of A is nothing but the integral of f d lambda. Lambda is the Lebesgue measure. Right, so you can do it. So it's you can either construct it from scratch or just use some general theorems to get it, but there is such a thing. Now, what if you want to prove that that type is consistent? Well, look, if xa in 2 norm is equal to 0, if you want x to be of large norm, what happens here? Well, here is A. A is the identity function. Now I'll draw it just as okay here. So let me just write it down. So what xa to what this means is that tau of A star x star xa is equal to 0. Right. So so if x tracially hits A in a very small set, in order for it to have a non-zero tracial norm, right? This is tau of x star x is equal to 1. Well, you see, we are integrating over a very small set here. So its norm would have to blow up. And remember, this is actually the important bit, that every variable comes with prescribed sort, and sort is a ball to which that variable belongs. So if the operator norm of x is less or equal than k, no matter how large k you choose, you can always find small enough epsilon so that this tau of this being 0 or even being less than epsilon will imply that the operator norm of x will blow up. Because if norm of x is less or equal than k, then tau of x star x is less or equal than that epsilon times the operator norm of x squared. So basically, no matter what k you choose, you end up with small enough condition which is not satisfied. So this was just a sketch of a proof. I'll just suggest that you go over details. All that I wanted to emphasize is that something else is going on here, right? So these tracially saturated cyst algebras are not saturated in the standard way, but their saturation is useful for other purposes. Okay, so here I don't really have an application if you just look at tracially saturated cyst algebras. And in the next example, we have an application. So I call it formulas revisited. So as I said before, I just didn't want to define just abstractly what formula is, what structure is, but just look at concrete useful examples. So this is our last one for the time being. So again, A is a separable cyst algebra. We have algebra of star polynomials. We define formulas. Now we have f of at plus. So again, you can stare at this definition and try to see what is the difference from the previous two definitions. And here it is, right? So I'm allowing both operator norm of polynomials and the two norm of polynomials as atomic formulas, right? So these two norms coexist in here. I should say for purists, for what I'm trying to do here, the right way would be to actually think of two different sorts, meta sorts, and talk about algebra with the operator norm and algebra with the tracial norm and have a quotient map. But this was simpler and it works. So I'll just stick to this version. And so once you define atomic formulas, everything else is the same. You apply continuous functions, you apply quantifiers. And again, this space has an algebra structure. Right, so here is the difference, right? So this, I'm allowing both of these. And what this language describes is pairs C and C mod out J. So the J is this tracial kernel ideal. And again, for purists, the quotient map is definable in this language. I haven't defined what definable means, so you can just ignore this if you're not a model theorist. But it's all in the EQ, as a model theorist would say. So this is really what I'm trying to describe, right? So simultaneously, we want to be able to talk both about cyst algebra with its operator norm and this tracial cyst algebra with this uniform two norm. And because uniform two norm is uniformly continuous with respect to the operator norm, everything is fine. We can think about, we can take this as a metric structure. So officially, this is the metric on the metric structure. And this is just a predicate, which is uniformly continuous, even Lipschitz. All right. So what do we do with this? Well, again, Walsh's theorem and countable saturation hold without any difference, without any modification. Proofs are the same, just induction on complexities. Right. So for Walsh, you use induction on complexity. For countable saturation, you take these partial realizations of your type and then use Walsh's theorem to chop them up and put them together, splice them into realization of your type. Now, here is a picture of what is going on. So here we have our cyst algebra A. So tracial space is non-empty and compact because A is unital. Now, what I have here is the completion in this 2U norm. This is actually not a trivial bit. Even if you take something as innocent as the car algebra, if you look at its unique trace, its bounded balls are not complete in the tracial 2 norm. And actually, I should be more precise here, of bounded balls of A. This is actually a sort of, well, almost a trivia question. The tracial cyst algebras are not complete with respect to tracial norm. Every norm bounded ball is complete, but the entire algebra is not complete, exactly because, oh, non-empty. Yes, thank you, Andrea. Right. So what did I, oh, oops. Thanks, Andrea. Yeah. Right, non-empty. So, I mean, basically, essentially, it's the picture from this previous slide when I was showing that type is not satisfiable. You know, in completion, in L2 you have unbounded functions, right? So because of that, this is not bounded. So anyway, so here we have this structure A and its tracial completion, and now ultra power. We are taking ultra power of this structure of A and the identity map into its tracial completion. And that gives us this pair. Here is A sub U is the norm ultra product, norm ultra power, and A super U is the tracial ultra power. So what we have here is that Walsh's theorem holds. So every formula that talks about these two structures simultaneously, how do you evaluate it? Well, you just pull it back to the original pair. Here is the original pair, A and A tracial completion, and just evaluate at each coordinate, and just along the ultra filter, you find limit, and that is the value. Also, this pair with the quotient map is countably saturated. Okay, so what can we do with this? So let's take a look at one example. Suppose A is a separable cyst algebra with non-empty unital. I should have said unital. With the non-empty tracial simplex. And now you have a separable subalgebra of its norm ultra power. And P is, right, as always, P is this quotient map from norm ultra power onto the tracial ultra power. And take a little a, which belongs to relative commutant. Let me draw a picture. So here is norm ultra power. Here is tracial ultra power. D is something separable here. Here is the image of D. And A, let's see if I, okay, there is a P missing here. So A is something here. It has the property that its image under the quotient map commutes with P of D. Okay. Now, and now we're looking at this structure, right? So our structure is norm ultra power, tracial ultra power, and the quotient map. As I said, I was cheating basically. Instead of saying this, I just defined this set with two kinds of formulas, but you know, you can describe both of these structures by using those two kinds of formulas. And now look at the type in the language that I described, which has these conditions. You see both norms occurring. First, the L2 norm of A minus X is 0, right? Which is really just a different way of saying P of A minus X is 0, right? So X, if we can realize it, it is going to be something that is modulo tracial norm the same as A. And what other conditions say? Well, they say that X commutes with everything in D, but now here it's operator norm. Right, note, in the original setup, A probably doesn't commute with D in the operator norm, Once you mod it out, once you mod out the tracial kernel ideal, commutation happens. But originally, they're probably not commuting. Right? So this type is an attempt to create something that commutes with everything in D on the nose in the operator norm, and yet has the same image in the tracial ultra power as little x. Now, type is countable because D is separable. You just need to fix a countable dense subset of D. More interesting claim is that type is consistent, right? And what I mean by consistent is approximately satisfiable. So let's see why that's so. Why did this happen? I have no idea. Sometimes, oops, sorry, I went too far. Okay. Just try to see where I am. I think I'm here, yes. Okay. So why is this type consistent? Well, so fix some f finite subset of D, fix some epsilon greater than 0. Now, we have this ideal Ju, this tracial kernel ideal. This ideal has an approximate unit. Just like any other C algebra. Okay, and that approximate unit serves to hide under the rug what we want to hide under the rug. So what do we know? So find in J sub U. So the following happens. If I take the commutant, the commutator of A and D, where D ranges over this finite set, if I multiply this by E, then the operator norm of this is at most epsilon. Right, I can do this because D is a finite subset. And I have this E which does it. So what do I do now? Well, let X be something like 1 minus E times A. Okay, then what is actually B? I guess it's a partial realization, so it's B. Now, what is P of B? Well, it is P of 1 minus EA, but E is in the ideal, right? So it is P of A. Now, what is, on the other hand, what is the commutator of B with D? Well, it is going to be less than epsilon, right? It follows from here, because B is just, oh, wait, hold on, did I need more? I need to commute with it. Thank you. So actually, I need something else. Thanks, Andrea, again. So you have fantastic timing. You just hear when I need you. So what exactly? Quasi-central. I need quasi-central. So what I need is E, which has two properties. This was property 1, and I'll squeeze property 2 here. So I also want the commutator E with D to be less than, and I'm not sure if I need something like probably epsilon over 2 times norm of A. And here I put epsilon half. right? So I don't even need the full power of a quasi-central approximate unit. All that I need to do is sufficiently commute with all of these d's, and really only with finitely many d's. So quasi-central is an overkill, right? But now if E approximately commutes with all of these, now I have this. Right? So the type is approximately satisfiable, and therefore, because the entire structure, this entire structure here is countably saturated, this type is realized in the structure. And realization is going to be something that, on one hand, has the same image as A in the quotient, and on the other hand, commutes with everything in D modulo the operator norm. Right, so what this gives is a reasonably elementary, at least for logician, proof of a very important result of Sato and Hirschberg-Jordan, that basically is if tracial simplex of A is non-empty, A is unital, and if you have a separable subalgebra of the norm ultra power, then okay, so this is stated in a slightly different way than from what I stated. We'll see why it is the same. Then the image of relative commutant of D in the ultra power, here is ultra power norm, here is D, and here is P of D. Here is the tracial ultra power. So if you look at relative commutant, its image is exactly relative commutant of the image. What we proved is we proved this implication, right? That if P of A lands here, then we can find the pre-image here, and the other inclusion is a triviality, right? If you commute and then mod something out, then you're still going to commute. Right. So this was one simple application to tracial ultra powers, but there are more. Okay, any questions? Okay, so let's go on. Here is an invariant that Eberhard Kirchberg defined back in 2004, I think. Here A is a separable sister algebra. You take norm ultra power relative commutant of A in the norm ultra power, and then you mod out the annihilator of the diagonal image of A in the norm ultra power. Right. So what's going on? You have A, you have norm ultra power. You embed A into ultra power diagonally, and then from it you define two algebras. One is relative commutant, and the other one is annihilator. Annihilator is actually ideal in the relative commutant. And now, if you mod this out, this is always a unital cyst algebra. And Kirchberg proved all sorts of very important results, applications to classification of this algebra. Now, if A is unital, then of course this here is just a trivial ideal, and f of A is just relative commutant. And I have to admit that I didn't really spend much time thinking about f of A. For example, it's not even clear to me what is, in general, what are its saturation properties if A is not unital. Based on looking at what Kirchberg proved with it, it has all sorts of properties that suggest that it is probably quantifier free saturated. Anyway, so let's just forget about non-unital case and just stick to unital case. So f of A is just this relative commutant here. Right, so this is what I just said. Okay. Now, here here is a question that Duza McDuff asked back in 1970. All ultrafilters are non-principal ultrafilters, and they are on N. Now, I haven't defined hyperfinite to one factor, but I don't have to define it here. Really look at the Carr algebra and look at the tracial alpha powers of it. These are really the same as, so hyperfinite to one factor is called R. This is really the same as the tracial alpha power of hyperfinite to one factor. So you can entirely state this in terms of C algebras, right? So McDuff's question translates as, are all tracial alpha powers of the Carr algebra isomorphic? Right? She asked this because they all look the same. And the question was, well, can you prove they're isomorphic? And Kirchberg, sometime later, asked analogous question for C algebras. If A is a separable C algebra, does f of A, right? So it's, I just think of this relative commutant, but it's more general, depend on the choice of the ultrafilter. Right? Notation suggests it doesn't, but it's not obvious. All right, and this is what I want to do next. I want to look at these two questions. And the answer is somewhat surprising. I'm sure that, well, definitely for Kirchberg, he didn't expect it. I guess that McDuff didn't expect it either. So it's a theorem of myself, Brett Hart, and David Sherman, that either of these two questions cannot be decided in ZFC. Right, so this is independent from standard axioms, and I'm going to prove one half of this theorem. Now, what does that mean? Well, basically, let's just look at what this theorem is saying. Theorem says that there are some models in set theory in which the answer is yes, they are isomorphic. And there are maybe some other models, not maybe, there are other models of set theory in which the answer is no. You can choose different alpha filters that give rise to non-isomorphic alpha powers or relative commutants of the same algebra. So I'm going to prove only the first half of it, which is the easiest half. It's much easier than the other theorem. So I'll just prove that under some axioms, all of these alpha powers are isomorphic. And also I'm going to argue that this is really the relevant half. You see, because intuition behind, I can guess what intuition was, that these alpha powers look very similar. And as you just saw, basically all of them are countably saturated and all of them satisfy Walsh's theorem, right? So alpha power of algebra is just a blown up version of that algebra with the same first order properties. They look similar. So we'll take a look at some axioms which imply that they are actually isomorphic. So I'm getting close to the end. So I'm just basically going to set the stage for what I'm going to do next. Any questions at this point? All right.
So is the answer clearly
okay,
false?
So I'll have to start with digression. It is not going to be obvious at all what I'm going to say next has to do with this theorem, but trust me, I know what I'm doing. So here it is. Okay, so actually I'll state first a spoiler before digression. So here is a classical theorem of Kiesler back from 60s. He didn't prove this for C algebras, he proved it for countable structures, but it's the same theorem, same proof. So if A is a separable C algebra and U and V are non-principal alpha filters on the natural numbers, then their norm alpha powers are isomorphic. Same for tracial alpha powers if tracial simplex is non-empty. And the theorem applies to tracial phoneme algebras and whatnot. So basically, the only important bits here are continuum hypothesis and separable, right? So assume continuum hypothesis, all ultra powers of separable whatever are isomorphic to one another. And this is purely model theoretic statement. Okay, so now comes the digression that I mentioned that apparently has nothing to do with the Kiesler's theorem. So-called back and forth method that definitely some of you have seen. I'm actually worried that maybe everybody has seen this already. So if that's the case, just let me know. I can just go on, but okay, I'll be quick. So here's definition. If you have a linear ordering, it is said to be dense, or sometimes people say dense in itself, to be precise, if between any two distinct points, you can stick another point. Just think the rational numbers, right? They are template for dense linear orderings. But also think irrational numbers, think real numbers, right? They're all dense in themselves. Okay, see, I misstated the theorem. So every two countable linearly ordered sets without endpoints, right? Because you can look at rationals in the 0, 1. Oops, don't you need the ordering to have? Yes, I do have. I have ordering linear ordering. So Pedro asked the question. Oh, countable. Yes. Sorry. Dense. Yeah, I stated definition, but then I forgot to add it here. Of course, thank you. Yes, thanks to Camille and John for pointing this out. So I'm not sure about Pedro's remark still. I need. Oh yes, sure. Okay, now. Oh, it should here. Is it clear, right? So the theorem should be saying every two countable dense linearly ordered sets without endpoints are isomorphic, right? So if you, endpoints can make a difference. And the proof is by this back and forth method. So just fix L less than and M less than. Now we can enumerate L as AN for n in n, can enumerate M as Bn for n in n. Now at any given stage, so what we define, let me just see if there is something else in chat. No. Ln finite subset of L, Mn finite subset of M, and Fn, which is an isomorphism between Ln and Mn, so that Ln is subset of Ln plus 1, right? So everything is increasing. If you take Fn plus 1 restricted to Ln, you get Fn. And also what I want is that An belongs to Ln, Bn belongs to Mn for all n, and also Ln, Mn, they're all finite. Right, so this is my setup. So what this means, let me just see if I can shrink this so that you can see. Right, so here is L. At any given stage, I'm going to have a finite subset of it. And in M, I have a finite subset. I have isomorphism between those finite subsets. And at any given stage, I need to extend this isomorphism by adding An to domain, An plus 1 to domain, and Bn plus 1 to the range. So how do I start? Well, I'll just send A0 to B0. And how does the inductive step work? Well, you see, what I have here is a finite subset of a dense linearly ordered set. So there are only finitely many possibilities for where An plus 1 can occur. It is maybe between two of the points. in which case I can just look at their images in B, and I know that because M is dense, I can pick a point between them, pick any point between them, and define this to be the image. If it is not between 2 points, it is to the left of all the points, and then because M doesn't have left endpoint, I can choose something there, and similarly for right endpoint. So that's the fourth direction. Back direction, you do exactly the same thing, just analyzing where Bn plus 1 sits, and just send it back. So basically, the only trick here is countability, because the induction is arranged in such a way that you're taking care of the nth element of each of the orders in the nth step. By the time you get to infinity, by the time you get your sets Ln and Mn to be infinite, both sets have been exhausted and you have an isomorphism. So some of you must have seen this argument. It has been generalized in all sorts of different ways. I'll just state exercise. Every two countable atomless Boolean algebras are isomorphic. Now, the reason why I'm saying this is why I was saying this is we want to see how this extends to non-separable structures. Right, so countable is same as separable. I mean, there are also separable versions of. Well, actually, right. So there is a nice one, right? So any two separable infinite-dimensional Hilbert spaces are isometric, right? It's also, it can be proved by back and forth method, or although you can just construct orthonormal basis. Never mind. So what I wanted to say is, if you want to construct isomorphism by a method like this, what sort of obstructions can you expect to happen at the first infinite stage? And the answer is all sorts of obstructions. So this theorem, okay, so it's false as stated here, right? So countable dense without endpoints. So this theorem, if you drop the word countable, it becomes false. And there are both trivial counterexamples in Aleph 1 and reasonably deep counterexamples of size Aleph 1. Which suggests that this idea of back and forth construction, once you reach countable stages, funny things can happen. And that is where countable saturation comes to the rescue. Okay, so yeah, I'll just stop here, and we'll continue on Monday, but I'll hang around if you have any questions. Okay, so no. Oh yes, Georgios. Aha, so I almost overlooked your hand. So please, Georgios, do you have a question?
Yeah, I wanted to ask, but yeah, sorry about this. We're gonna, you can hear me, right?
Yeah, I can hear you, sure.
Yeah, so we have to go a bit way back. When you said that, okay, so we assume that the trace space of a sister algebra is non-empty, then it is, you had that it's stably finite, but you added simplicity, right? What was the example that you were thinking of?
Oh, just to take something stupid, like to take M2 direct sum with O2. I mean, to take any, any tracial system algebra and direct sum with anything that is not stably finite.
Right, but if you have, so wait, so if you have a trace on a sister algebra, then it's finite, right?
Yes. But trace is just going to vanish on that infinite summand. right? You have a trace. If your algebra, let me just go back so that I can write here somewhere. Oops. Right here. So if your algebra is of the form M2 of M2 of C direct sum with whatever, take O2. If I take a trace, the trace of AB just to be trace of A, right? This is a tracial state. It annihilates O2.
Okay, thank you.
Okay. Yeah, I'm not sure how I overlooked this when I was preparing. Okay. Any other questions? So Georgios, your hand is still up. Okay.
Fixed it.
Yeah. Any other questions? Okay, so usually there are more questions than today. I don't know if this lecture was less inspirational or I just said everything. There was nothing else to ask. But anyway. All right. Okay, great. So I'll see you on Monday and we'll continue with the countable situation.